Hello, my name is Neal, and I'm going to be discussing my proposed PhD project on the high confidence modelling of particle resuspension. So in terms of the motivation behind this project, resuspension is the process that occurs when a deposited particle becomes detached by a force and then transported back into the atmosphere. And it's a process that happens all around us due to stuff like wind and moving vehicles, but we're particularly interested in it when the resuspended aerosols are hazardous to us. So we have some examples on this right hand side here. And the reason that resuspension can be so problematic is because it's known to increase the distance that these aerosols can spread, and also the time that somebody might be exposed to one of these aerosols. Yet in spite of this, resuspension is very rarely included in the dispersion models we use to assess the risk associated with these aerosolization events. And the reason behind that is that we don't know enough about resuspension currently to reliably model it. And this is something that we really want to change during this project. And so to do that, we're going to develop an existing model for particle resuspension, known as the rock and roll model, which has been highlighted already as a model that is suitable for further development, but in its current form has quite a lot of assumptions, simplifying assumptions attached to it. And so we see the model, a schematic of the model on the right hand side, where you have a spherical particle. In one direction you have some force due to the detachment forces, and in the other direction you have the adhesive forces that are attracting this particle to the surface. And if the detachment forces are greater than the adhesive forces, this particle begins to roll and will eventually detach from the surface. And so to improve this model, we're going to use a stepwise method where we have some prior experiments to understand resuspension a bit better, and hopefully use some new knowledge to incrementally improve the model. And after each new addition to the model, we're going to experimentally validate it to ensure that it keeps giving reliable results. And our initial focuses are going to be on trying to add different particle morphologies to the model, so not just using spherical particles, and also look at how surface roughness can affect the resuspension rates. And so finally, in terms of the experimental methods we might use to achieve the goals on the last slide, we'll be using atomic force microscopy to determine the adhesive forces between particles and different surfaces. But in order to use AFM, we'll be requiring particles to investigate. And this is where a novel method from the University of Bristol comes in, which is the falling droplet chain equipment on the right hand side, where essentially you dry a solution in very specific conditions to end up with particles of a controlled morphology at the end. And this can be used to create the samples for AFM analysis. And then finally, in terms of model validation, we can use a wind tunnel to look at the number of resuspension events that occur in specific scenarios. And with that, I would just like to say thank you very much for listening.